Hey, Vlad here, devinsideyou.com. Welcome to the final video in the Homegrown collection series. Man, I can't believe that I'm saying this. I recorded the first video for the series almost a year ago, and in that video I said that Scala 2.13 is coming out soon with the entire new Homegrown collections redesign. And now, almost a year later, it's still not out, but it seems to be super close, so fingers crossed. As always, we're in the Ubuntu virtual machine, which is fully maximized, and we're still using Sublime Text, which is the editor of my choosing, which is also fully maximized, with a wonderful plugin called Terminus, which runs at the bottom over here, which emulates the entire terminal for us, which we use to run SBT, which we use to rerun the tests every time we save the file. In the previous video, we have seen a few ways of generating streams, and then we generalized that into the function called unfold. And today we're going to continue with that and have a few more examples of things, but these ones are going to be a bit harder to squish into unfold. And by the way, in case you didn't notice, I sometimes like to introduce things in very crazy and weird ways, like streams being timelines and fourth dimension and whatnot. So today we're going to come down back to earth and have a more typical examples for streams like Fibonacci's, factorials, prime numbers, and so on. This video should be much shorter than the other ones, and also by the end of it I'm going to say a few things about what's going to come after the Homegrown collection series, so you might want to stick around. Alright, as a refresher, let's start with a few examples from the previous video. These are going to be the examples that you're already familiar with. So we're going to start with numbers like this. So we're going to have a lazy val once, which is a timeline of ints, which is just going to be a 1 prepended to a bunch of ones, and this has to be a lazy val because we're inside of this test. In fact, if I'm gonna do this, I'm just gonna run the test. I have no idea why it takes forever. I'm also gonna take these two lines and I'm gonna, come on, really? Oh my god, look at this. It just took 20 seconds to compile these two lines. I have no idea what happened. I wanted to show you that if we go up like this, then all of a sudden it doesn't need to be a lazy val like that. Okay, so hopefully it's gonna be faster now to compile everything. Done compiling. Okay, that was a bit faster than before. All right, so as you can see, it doesn't need to be a lazy val. It only needs to be a lazy val because we're inside of this. So if I remove this lazy, it's not going to compile. There we go. All right, so let's have it as a lazy val, and let's go over here and say once, take 5, and it should be a timeline of 1, 1, 1, too many commas. 1 and 1. Okay, like this. Scala reform fixed everything for me. It should be green in just a few seconds. I have no idea why it takes forever to compile now. It's just like one more line. All right, so let's go over here. Let's do once 2. It's a timeline of int. And in the previous video, we have created these awesome helpers. Okay, so we're going to do the same thing for this one. So it's going to be once 2 like this. Let's see. Let's also have a function called ints, and it's going to be seed of int, timeline of int like this, seed prepended to ints of seed plus 1. And so if we take this, bring it down, let me create a bit more space. So if we do ints that start with a 0 like this, we take 5, should be exactly the same as before. We can also have a different version of it. So if we go over here, obviously I should change that. 0, 1, 2, 3, and 4. We're starting with a 0, so 5 of them is going to end with a 4. So I copied that, so I'm going to paste it over here so we can say ints 2 over here. And now similar as over here, we're just going to say seed dot timeline, and we're just going to have a plus 1 over here, right? So I'm just going to copy that, bring it down over here, and 2 like this. Now the next one, however, is going to be a bit new and a bit weird and a bit hard to squeeze into an unfold. So I'm gonna do this. I'm gonna bring it down. Okay, I'm gonna call it ints 3, and at the end it should behave exactly the same way, like this. Okay, but now the implementation is gonna do this. It's gonna say, okay, let's start with the seed because that's what the seed is for, and then we're gonna take the ones that are at the top over here, the ones over here, just a bunch of ones, and we're gonna zip it. We're going to zip it with ints 3 again, with the same seed. And now we're going to map that to case. And on the left, it's going to be a 1. And on the right, it's going to be an ACC. And so we're going to go over here and take the ACC and do plus 1. And let's see what comes out. If I made any typos. I didn't. Okay. And just to play around with this, let's say ints 3 of 3. And let's take 4 of them. Then we're going to start with 3, 4, 5, and 6, just for fun. In fact, I'm going to throw out this line just so that you know that it still works. Okay, let's throw this out like this. Now, if this is the first time that you're seeing something like this, then it might be really hard to visualize. And so I'm going to help you with that. The easiest way that I think is the easiest way to visualize this is to forget everything you know about programming, and instead of trying to trace the entire stack, the entire call stack in your head, just as I said, forget everything you know about programming and try to simply verbalize this in English. Okay, so what are integers? Integers are a timeless stream of ints that start with some seed. In our case, it's a 0. Prepended to an endless stream of ones, okay, zipped with some other stream of numbers. This is the key. The key is to visualize this as if this was a completely different seed of numbers. In fact, what you can do is you can go over here and use a completely different stream of numbers. And I believe now it's actually kind of easier to visualize, okay? So it's just basically a bunch of ones and a bunch of numbers, and they're zipped together, right? And then you have on the left, you always have the ones, and on the right, you always have the numbers. So in the beginning, because it starts with a seed, then this is going to be 0, right? So 0 plus 1 is going to be 1. So it's going to be this 0 prepended to the 1. In the next iteration, it's going to be 0, 1 prepended to, there's going to be a 1 over here, 1 over here. 1 plus 1 is 2. In the next iteration, it's going to be 0, 1, 2. And then we zip the ones with whatever comes here over here is going to be the 2. Okay, so 2 plus 1 is going to be 3. So this is how you generate the numbers, right? So you can take any of these streams. Ints, I believe we already have. Yeah, so we have ints. We can work with ints. We can work with ints 2, and we can also work with ints 3. And this works because there will be always enough ints generated from here, which are necessary for this entire thing to work. Now we will keep working with integers all the time. So let's go to timeline, to the companion object over here, and let's where are we going to put it? So we have unapply, apply, we have folds. Yeah, maybe let's put it above the folds, over here, right? So between the apply and between generate same. So we're going to have a case object. Doesn't have to be a case object, but the error messages are going to look better if it's a case object because it's just going to generate a toString for it. So we're going to have final def ascending from int. It's going to be a timeline of int like this. So I'm going to say from timeline. Sometimes I call it from, sometimes I call it seed. Okay, so this is ascending, and we're not going to use this one, but just because we have ascending, we're also going to have descending like this. Okay, let's go and add a tiny test for it. So now we can do timeline int ascending from 0. We can take 5, and it should be the same as over here, like that, like that. Let's duplicate that. Let's say descending. We're also starting with 0. We're also taking 5s. 5, it's actually, let's not start with a 0 because I don't want you to get confused. Let's do 10 and let's do 3. Okay, so that's going to be 10, it's going to be 9, it's going to be 8, right? So it's 3 of them, 10, 9, 8. Let's also, just for fun, create another helper that will generate a range. So we're going to call it inclusive. It's going to take a from, and it's going to take a to, and it's going to generate a timeline of int like this. Let me scroll down a little bit. Maybe that's too much, but it doesn't matter. So if from is greater than 2, then we're done. It's going to be timeline end. Otherwise, we're just going to take the from, prepend it to inclusive from plus 1, and 2 stays the same. So that's going to be inclusive, not in line. It's going to be inclusive like this. Let's copy that thing. Let's save it. Let me paste it over here. So that's going to be exclusive, exclusive, and there's going to be an equal sign over here. All right, let's go and write a test for these. So we're going to go over here. I'm going to say timeline dot int dot range dot inclusive like that. It's going to be a 5 and a 9, and it should be a timeline of 5, 6, 7, 8, 9. So it includes the 9. And how did I call it? Oh, I actually wanted to put it into the object range over here like this. So it's int and range like that. Okay, so this is the inclusive one, and that's going to be the exclusive one, and the exclusive one is going to contain the 9 like this. Okay, and let's also make sure that if we swap the 9 and the 5, so if we do int dot, not ints, int dot range dot inclusive, oh, come on, inclusive, so if we swap the 9 and the 5, then it should be a timeline dot end like this, should be right, inclusive and exclusive like this. All right, cool. So now we're pretty much done with this example. We know how to generate numbers with this weird fashion, and also with the folds and with the unfolds and so on. Next thing that we're going to do is we're going to play with factorials. So we're going to have factorial over here like that, and we're going to start with a helper. I'm going to call it a sort. A sort takes in the timeline of int, produces a unit. In fact, it produces the Scala test assertion, but it doesn't really matter. So what we're going to do is we're going to take 10 of them, 10 factorials, and we're just going to hard code them. 1, 1, 2, 6, 24, 120, 720, 5040, 40320, 36288, like this. Let's see if that compiles. It should. All right, so let's go and have a factorial timeline, which is going to be a timeline of ints, and we're going to implement this in just a second, but at the bottom we're going to go and assert that this factorial timeline is actually a factorial timeline. Okay, so we're going to go over here, and we're going to have a recursive factorial, which is a typical factorial implementation. In fact, I'm also going to use a tail recursive function for that. Okay, so it's going to be defined over there, and we're going to create a timeline over here, int ascending from 0. We're just going to map every number to recursive factorial. Okay, and the recursive factorial is going to have a loop over here, def loop, which is going to be tail recursive Scala annotation dot tail rec, and by the end we're going to call this loop with end and 1 like this. So we're going to go over here, so the end is going to be an x, that's going to be an accumulation like this. Okay, so we're going to say if x equals 0, then we're just going to return the accumulation. Otherwise, we're going to call the loop in which x is going to be x minus 1, and the accumulation is going to be accumulation times x. Let's see if I made any typos, and I don't believe that I have. All right, okay, so this is a typical recursive implementation. In fact, we just need to see that it's green like that. Is that enough? Yeah, that's enough. All tests pass, success. Cool. So we have more space like this. So this is a typical recursive definition of factorial, which is also tail recursive. But streams are actually co-recursive. So instead of generating numbers and then just sort of like almost filtering them, I mean, we're not filtering, but we're mapping every number, we can actually generate factorials right away as we go. So instead of generating numbers and then mapping them, we can just generate factorials. Okay. So I'm going to collapse that, and I'm going to say over here that this is going to be factorial timeline 2. It's going to be a timeline of int. In fact, hold on, I'm going to do this like that. Okay, and in the end, I'm going to assert the same thing about this timeline. Okay, like that. Okay, so over here we're going to have a definition which is going to be called co-recursive. Co-recursive factorial starts similarly, ACC int. In fact, maybe I should call it x. I'm going to call it x. Okay. Oh, no, I'm not going to call it. No, maybe I should, because I want it to be sort of similar like over here. So we have x ACC, and over there we're also going to have x and ACC. Okay. So it's going to be a timeline of int equals something, and then at the bottom we're going to call it co-recursive factorial. I'm going to say that x is a 0 and ACC equals 1, right? So the factorial of 0 is 1. Okay. The definition is going to look like this. We're just going to take ACC, and we're going to prepend it to co-recursive factorial of x plus 1, and we're also going to take the x plus 1 and multiply it with ACC. All right, so we're going to do multiply it with ACC, and we're also going to have a tiny helper. Whoops, what did I press? I pressed pages up. Okay, so we're going to have a val next, which is n plus 1, and we're going to use it over here twice. next, next, like this. Okay, so we're gonna have next and next time ACC. In fact, I believe it's easier to read it like this: next and ACC times next, like this. All right, where do we have this n? X. It's not. Yeah. Okay. So there we go, and it should be green in just a few seconds. And now we're gonna have a third version, which is gonna look similar to this one. Okay. In fact, maybe we should just copy that. I'm gonna copy that. I'm going to bring it down over here. Let's collapse this one like that. I'm gonna paste that, and this is going to be called. This is going to be a lazy val. It's not going to be int3. It's going to be factorial timeline 3. Okay, it produces a timeline, so we don't need the seed like this, like that, because we know that it's just going to start with 1. Okay, at the bottom, let's not forget that we're actually going to test it like this. Okay, so what are we going to do? Well, we're going to take the timeline. Okay, and over here we're going to zip it with numbers, right? So we're going to have timeline.int AC from, and we're going to start with 1. Okay, because we want to the first thing we want to do is we want to multiply the 1 was the 1 over here. All right, so we zip with a factorial 3, we map, and now over here we don't have the 1, we have the x, and it's going to be x over here, and we're just going to multiply them. Okay, let's see if I made any typos, and it looks like it compiles just fine, and it's going to be green in just a few seconds. All right, now visualizing that, you're going to use exactly the same trick, right? So what is a factorial? Well, factorial is a zip of 2 streams. One stream, it just has the numbers, and the other stream just has the previous factorials, right? So what are you going to do? You're going to take the number from here, you're going to take the previous factorial over there, from there, and you're just going to bring them together. And the same as before, just look at this as if it wasn't this one. Just look at this as if it was another one, right? So we can just take the second one. It should behave exactly the same. It should still be green, and we can do it with the first one, and it should also still be green, right? But obviously you wouldn't do it. You would do it more like this and confuse everyone around you. All right, so the next thing that we're going to do is we're going to go and we're going to use write the same thing basically for Fibonacci. We're going to go and say test Fibonacci like that, and we're going to start with the same assert trick. So we're going to take assert, and we're going to go down over here and paste it, and the first 10 Fibonacci's are going to be 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. Let's see. All right, so the first thing that we're going to do is we're going to have a val Fibonacci timeline of int is going to be, it's going to be the same trick as before. Okay, so we're going to go over here, I'm going to say assert Fibonacci timeline. We're going to have a recursive algorithm over here, recursive, not factorial, Fibonacci. It's going to take an n, it's going to be an integer, it's going to produce an int like this. There will be some sort of implementation over there. We're going to start with a timeline of numbers, so we're going to have timeline int AC from 0, just going to map it to a recursive Fibonacci like that, and the implementation is going to contain a loop, right, with x, which is going to be an int. It's going to be Scala and notation dot tail rec, and at the bottom we're going to call this loop with n and the first 2 Fibonacci's, which is 0 and 1. So we're going to have an x, we're going to have ACC1, which is an int, ACC2, which is an int. We're going to produce an int. So if x is a 0, whoops, it's a 0, then just return the ACC1. Let's scroll down a little bit. Otherwise, if x is a 1, then we're going to return ACC2, and otherwise we're going to loop again, and our x is going to be, hold up, our x is going to be x minus 1, ACC1 is going to be ACC2, and ACC2 is going to be ACC1 plus ACC2. Let's see if I made any typos, and it looks like I didn't. It's green. Awesome. All right, let's do the same trick as before. Let's collapse that. Let's go over here. Let's have val Fibonacci timeline 2, produce a timeline of ints like that. And at the bottom, let's not forget to assert Fibonacci timeline 2 like this. So over here, we're going to have a co-recursive, not factorial, Fibonacci like this. It's going to take a few things. At the bottom, we're going to call it co-recursive Fibonacci with x equals 0 and ACC is going to be 1. We don't need that over here. All right, so the co-recursive Fibonacci is going to get an X, which is an int. It's going to get an ACC, which is an int. So I'm using the same naming convention as before for factorial, but in fact, we're going to rename them in just a few seconds. So it's going to be X prepended to co-recursive Fibonacci of ACC and X plus ACC, right? So this thing is that the first thing becomes the ACC and the second one becomes the sum. It's the same as before here. The first one becomes the, becomes basically the second one, and the second one becomes the sum. Okay, so let's see if I did it right, and I probably did. Yes, I did. So now we're just going to go and rename a few things, right? So the X is obviously the A. This is A, and this is the B, whoops, B. Okay, so Fibonacci starts with a 0 and 1. It's just a 0 prepended to Fibonacci of B and the sum of A and B. Okay, like this, and there we go. And by the way, I have no idea why, but Scalariform inserts 3 spaces over here, and for some reason it doesn't do that over here. All right, for the last trick, let's copy the factorial, which is this one. Let's bring it down. Paste that over here. Let's rename it to Fibonacci 3. No, Fibonacci timeline 3. All right. Now the trick is that Fibonacci it has 2 seeds, right? It has a 0 and the 1, so we have to start with a 0 and the 1, and therefore it will also need 2 timelines. So instead of just this one, it will use the Fibonacci timeline. Okay, like this one. Okay, so this is going to be the A, this is going to be the B, and this is going to be the A plus B. Okay, now if you look at this, there's a bug there, right? So if the A comes from this timeline and the B comes from this timeline, then, and if it's the same timeline, then it's going to be 0 over here and the 0 over here. This is not what we want. We want the first timeline to start with a 0, but the second timeline we want to start with a 1. So all we need to do is we need to go over here and we need to say tail, give us the tail. So it's actually the first time, in this 6 videos that we're actually using the tail. And verbalizing that is the same as before, just, use this mind trick that, these are completely different ones, right? So ignore this whole recursion thing, just pretend like these are completely different ones. There's no 1 over here, right? So Fibonacci 2, Fibonacci 1, you can, convert them any way you want. It's going to be 2, you can also, yeah. Anyway, let's use the third one like this, because at this point I believe that you should be able to visualize that anyway. All right, the last thing that we're going to do is primes. Primes are going to be fun. In fact, primes are going to contain one very, very tricky scenario. So we're going to have primes like this. Okay, we're going to have the same assert like this. Assert primes. Paste it over here. So the first 10 primes are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, like this. Okay, so let's implement in the same way as we did before. We're going to have primes, timeline of int. We're going to have some sort of implementation in just a few seconds, like this even. And at the bottom, we're going to say assert primes timeline. Okay, so the implementation is going to be like this. We're going to have the recursive is prime. It's going to take the n, which is an int, produce a boolean. Okay, like this. It's going to be a little bit different, right? So in the previous one, for the factorial, for example, in the very first one we used map, but in this case we're gonna filter, right? So we're gonna have a bunch of numbers. In fact, let's write that part right now. So we're gonna have a bunch of numbers. int.asc from 2, and we're just gonna filter now recursive is prime. No, like this, recursive is prime. Okay, so now we're gonna have a loop over here. It's gonna be tail recursive scala.annotation.tailrec, and at the bottom we're just gonna call loop with n minus 1, right? Because we're gonna, a prime number, it only is divisible by itself, so there's no point in putting an n over here, right? Because the first thing that is gonna happen in the loop, we're gonna check if it's divisible, and every number is divisible by itself. So we'll start with n minus 1. So we're gonna have an x over here, right? Which in our case, in the beginning, there's going to be a 1 over here, right? So 2 minus 1 is 1, okay? So it's going to be a 1, produces a boolean, right? So we're going to say if x equals 1, then it's a prime number, right? So 2 minus 1 is 1, therefore the 2 is a prime number, okay? Otherwise, if n divided by x is 0, right? So if it's divisible, then it's false. So it's a composite number if it's divisible. And otherwise, we're just going to try again with the number that is 1 less until we reach the 1, and it will return true. Let's see if I have forgotten something. It looks like I didn't. Awesome. All right, now the next one is going to be the most confusing one. So let's go and let's not collapse it. Let's go and here have, okay, lazy val primes timeline 2. It's going to be a timeline of int. It's going to be something, right? And at the bottom, we're going to do the same assert thing. Primes timeline 2. Okay, so in here, we're going to have still a recursive thing. I'm going to have recursive is prime, right? So it's still recursive, and comes in here, boolean comes out. Okay, and at the bottom, and this is going to be a little bit different this time. So at the bottom, we're not just going to call it with numbers. We're going to call it with the numbers that start with a 2, right? So it's going to be a 2, right? Like this, timeline int AC from 3, like this. Okay, and we're going to say filter recursive is prime 2. In fact, I want to test this in the end because I believe that we could also just do we can also just start with a 2. I believe this should be fine as well, but let's test this one first. Okay, let's do this one. Okay, so this is going to be a very interesting one because inside of it we're also going to have a loop. In fact, I'm going to copy this loop over here. It's not going to be tail recursive, but I'm going to copy this loop like this. Okay, so this loop is not going to get an x. What this loop is going to get is already a timeline of primes, right? So these are not just numbers. These numbers are guaranteed to be primes. And so in the very beginning, when we call it, we're going to call it, and this is the trick, we're going to call it with this lazy val. In fact, for now, let's not do it with this lazy val. Let's call, you know, it needs a timeline of primes. So let's just take this one, primes timeline 1. So let's just go and where is it? Over here, right? So in the beginning, we call it with a timeline of primes. Okay, so this thing is going to stay the same, but our axes are going to be called p's, right? Because they're primes, so let's call them p. Okay, and over here, this part is basically going to stay the same, right? So we're just going to take the primes and we're going to take the tail. Okay, but this part is going to be a little bit different. Okay, so this part is going to look like this: if n is smaller than p times p, like this. All right, let's see if I have forgotten something. Recursive is prime 2. Okay, I called it 2, like this. Oh yeah, I've forgotten the most important thing. So this whole thing is going to be primes.hat, right? So we've forgotten actually to use hat. So we're using the tail over here, we're using the hat over here, right? So this is an option of the hat. So we need to say to ask it if there is a prime over here, if it exists with this thing. Okay, like that, like this. Okay, let's see. All right, it's green. Now, if n is a composite number, then it will for sure contain a factor, which in this case is p, right, which is a prime. Then it will contain a factor that is less than or equal to the square root of n. And if that's the case, then the square root is going to be, you know, the square root of that factor is going to be less than n. However, if it is greater, which is what this condition is checking, right? If the square is actually greater than n, then it can't be composite. And if it's not composite, well, then it's a prime. And therefore we return it true. And this is mutual recursion over here, right? So instead of calling this primes timeline, we can call the same one, lazy val over here, primes timeline 2. Look at this. I'm going to collapse this one, right? So we have a lazy val. Inside, it uses the inline def over here, the inner def, and this inner def uses the lazy val, right? So if I open it up again, it uses this lazy val, and it still works. And in fact, I believe that it should also work with this one. Like this, it should work. It's the same thing. No, it doesn't. Oh my god. All right. Well, that was a nice theory to try for some reason. All right. Oh yeah, because it's not like this. It's not like this. That's not the same thing. Like this is the same code as this one. Okay. So we're filtering only the right part, right? We're filtering only this part. Okay. So that should break now. This should break in the same way as it just did. Yeah. All right, so we remove that, and we remove that, and we remove that. Okay, and one thing, you know, every time you see mutual recursion, I want a light bulb appear above your head with the, you know, handwriting all over it saying trampolines, right? So every time mutual recursion should associate in your head with trampolines, but we're not going to do trampolines over here because I already have videos about them, and I still have nightmares, right? So we're not going to do this because it's you know, it's complicated enough, and this is the last video. Now, arguably the most canonical algorithm for streams or for, you know, filtering prime numbers is the sieve of Eratosthenes, and I hope that I did not butcher his name. So if you look up into Wikipedia about the algorithm, one of the things that you will notice is that this algorithm, first of all, it doesn't check for primes, it generates primes. And so the way it is described on Wikipedia or everywhere else is that you need an upper bound. So you need to say generate numbers until, I don't know, 200 or something, right? For streams, you don't need an upper bound because it will just keep generating until you run out of memory or patience, whatever comes first. Okay, so let's go and implement it real quick, and if you have never heard of it, I'm gonna explain it to you while, you know, during the implementation. Okay, so we're just gonna duplicate that, and that's gonna be the third one. So we're going to have a lazy val pt3 like this, and it's going to be a timeline of ints, and it's going to look like that. So we're going to have a sieve over here, and at the bottom we're going to call this sieve. I'm going to call this sieve with a timeline int ac from 2. So in this case, actually this thing is going to work. Okay, so what we're going to do is we're going to tell the sieve that it's going to get the timeline of ints, timeline of ints, and we're going to say timeline match. Let me scroll down a little bit like this. All right, so if we're giving it the empty timeline, then we're done. Timeline dot end. Otherwise, timeline dot not empty if it's a recent event, and the following events like this. And then we're going to do the following. Okay, so we're starting with the 2. Okay, so the sieve of Eratosthenes works in such a way that you just you know, you take that number, right? If the number is already given to you, then you know that it is a prime. So you just take it and say run. Okay, so we're generating primes, right? So this one is already there, so we just prepend it to something. Okay, so the 2 is already a prime. Now, what are we going to prepend it to? Well, we're going to prepend it to a sieve again. Well, what are we sieving this time? Well, I guess we're sieving the rest. Okay, we're going to sieve the rest, right? But from that thing, we need to remove the duplicates of the 2. So in this case, we're just going to filter whatever. So this is our 2 over here, right? This is our 2 over here, right? Right, like this. So we're keeping only the ones that are not the duplicates of 2, and that's actually it. Let's see if I made any typos. And it looks like I didn't. It's green. That's the entire algorithm, right? So you start somewhere. You start with a prime, with a 2, right? And then you just recurse, and you just go and you remove everywhere the duplicates of the 2. So you keep the ones that are not divisible by 2, okay, on the tail, right? So you start with a 3. Is it divisible by 2? No. So you keep it. Then you go to the next one. It's the 4. Is it divisible by 2? Yes, so you throw it out. Now we're pretty much done with these examples. I just want to show you one thing, because there's a tiny improvement that we can do. I left it out on purpose in the like 2 videos ago, and it has something to do with the implementation for filter. So what I'm going to do is I'm going to copy that whole thing like that, maybe even the assert. No, we don't need the assert actually. Let's copy the assert as well. Okay, so I'm going to copy that, and I create an environment over here, because in this case, so it has something to do with the initializations. Okay, so let's save it. So what we're going to do is we're going to go and look at our primes. So we have 29 over here, right? So the events occurred should be 30. Events occurred should be 30. Where are we? Over here. Okay, so after this assert, events occurred should be 30. Okay, but what happens is that events occurred is actually not 30. It is actually 0. Why is it 0? Oh, it's 0 because we're not side effecting anything. So instead of this thing, we're just going to call ints from 2, and ints is going to be over here. It's just going to be def ints from int produces a timeline of int, just like this, side effect from, like that, ints from +1. Okay, so this is not the error message that I wanted. Let's see. This is the error message that I wanted, 190. In fact, in my script, it's not even 190. Doesn't matter. Let's put a 190 in there. 190 in there, and let's see if we can get it down to something else. Okay, so now it's green, and now if you go to filter in the timeline, so if you go to filter, and the same thing is going to happen to take while over here. If you look at over here, ACC is being used only once, right? It doesn't matter in which branch we go, it's going to be used only once. But if we end up in this branch, then the current is used at least once, right? So in some cases, it's used twice. In some cases, it's used only once if we're ending up in this branch. So we can memorize it, okay? So we can go over here, we can say val memoized current equals current. So now we can go and use it over here and over here. And we can do the same thing for take while, by the way. So I can just duplicate that, bring it down like that, and also like that. Copy that right here, and current is going to be memoized current. Okay, so now this should bring this number down a little bit, right? So it's not 190 now; it's 61, which is good, right? So now it's going to be 61. And if we look at our sieve, right? If you look at our sieve, we're using this recent event unsafe run. We're doing it twice. Okay, so we can also memoize that. So I'm going to copy that, and I'm going to call it val. It probably doesn't need to be a lazy val memoized. Maybe it needs to be a lazy val memoized recent event equals recent event unsafe run. So let's do this, and let's go over here. Let's see if it needs to be a lazy val. Maybe it does. Yeah, it does. Hold up, lazy. Okay, that was not the issue. Hold up, let's remove that. Let's actually read the error message. That should help. If you scroll up, it probably just brought the number down from 61 to around 30. Yeah, 31 for some reason. For some reason, there's some off by one thing there. But in any case, this doesn't need to be a lazy val, I believe, right? So let's go down, and it is green. Awesome. Now, in terms of code, this is actually all I got for you today. So let's go and commit that real quick. So I'm just gonna add everything, and I'm going to commit -am, and that's going to be video 34 streams. I'm going to call it typical examples, right? Like this. Commit and push, and there we go. Let's go check it real quick. Click here, typical examples, right? So we just had the ints, the range. So this is the thing that we added to the timeline companion object. We fixed the filter, we improved the take while. We improved the filter, improved the take while, and then we just have seen how to generate numbers, factorials, Fibonacci's, and primes like this. Cool. All right, so let me say a few things. First of all, streams, even though they look really awesome, there's nothing perfect in this world, and I will never stop reminding you guys every time I introduce you with some new concept or I show you some new trick. There's nothing perfect in this world. Everything has downsides, so we're going to go through a few of them real quick. The first thing being is that the same way as I/O, streams are designed in such a way that you compose them in your entire program, and only at the very, very end, at the so-called end of the world, you drain them. The same thing with I/O, only at the end of the world, you call unsafe run on them. Now, the problem with that is that every developer on your team, including you, the tired you, or whatever, nothing's going to prevent you from calling unsafe run somewhere in the middle of your program, or draining your stream somewhere in the middle of the program. So you need to be very careful, and especially if you're running if you're doing a concurrency, if you have multiple threads, they should never drain the same stream, right? So you should have only, one end of the world, so to say, or at least they shouldn't share the stream. In case this is not obvious, that last point was sharing the streams that drain the same stream. That one is only important if you have side effects inside of your stream, right? So if you're working with your streams as if it was just a data structure, right? So it's just numbers in there. There are no side effects in there. Then of course you can drain the stream from both sides. It doesn't really matter. Which brings me to memoization. At least the way we implemented streams, it is not visible from the types whether the stream is memoized or not. By the way, if this was a production level library, the same as I said when I did this, I would have never implemented it like this. I would have completely two different data structure, probably even without any trades between them, to make it clear that in one case this is just a data structure, this is just a collection, so we can memoize things, and in the other case, this is a driver for an entirely new paradigm. Okay, so we have them as completely two different things, and maybe with functions that convert one into the other. And also memorization on its own introduces more memory. I wanted to say issues originally, but basically it consumes more memory, right? So if you memorize things, you consume more memory, and this is one of those things that Streams actually wanted to mitigate for us, right? So the canonical example for Streams was, let's not read the entire file into memory. Let's read it line by line. But if you memorize that, then you memorize the entire file, right? So you don't always want that. Yet another typical critique on Streams is when designing what I like to call encapsulated procedures. A canonical example for this is opening the file descriptor, streaming the lines from that file, and then the last thing is to close the descriptor. And to be perfectly clear, I mean a stream which describes all of these actions. So the first element of the stream is the action open the file. All the others are, read the lines and map them to something, and the last action in the stream, right? So at the very end of the stream is to close the file. The problems arise if you start filtering the stream, or if you take while on the stream, and then you never reach that action that actually closes the file descriptor, right? So care needs to be taken when designing systems that work like this. And I'm sure that there are many other pitfalls, but these were just the 3 or 4 whatever you just said are just the ones from the top of my head. All right, now let's finish with the streams, and let me say a few things about what's going to come next. First of all, I try to have every commit on record, but probably I will have a few more commits that are not going to be worthy of videos. One issue that I have is that right now we're depending on the RC version of Scala on the release candidate. So once the actual Scala, Scala 2.13 comes out, I'm going to create a commit. Also, I'm going to clean up a few things. I'm going to remove a few main methods. I'm going to probably remove the whole CPS stuff. And if you still, trying to find this information, it's all on GitHub, right? It's just buried somewhere in the history. Also, there is a slight chance that at some point in the future, I'm going to come up with some other video that is related to collections, and I might decide to also link it into this playlist. So in fact, the video that you're watching right now might not be the final one. All right, so what comes next? Here's the thing. I started this channel 2 years ago, and as the description of the channel says, I wanted to make the world of professional software development accessible to anyone. In my head, someone would stumble on my channel without any prior programming experience, and so I wanted to take them by hand and sort of create a path for them, for a learning path for them. So all of my videos until now, all the 2 years, which is over 100 videos, they have this sequential nature to them. So every video that you watch is sort of a prerequisite for the next one, and for the next one, and for the next one. In fact, now that I think about it, it's sort of like a visual book. Now, as I just said, for over 2 years, I believe that I actually succeeded with that. At first, I started with a motivational playlist that explains what you're getting yourself into, and also that you will never stop learning, because especially in our industry, things develop so fast that you basically, you just never stop learning. And so the next thing that I did was I created a tiny playlist in Python, and by the end of this playlist, I revealed that I actually never have programmed with Python before. And so if I could learn, so can you. After a few filler videos, it was finally time to introduce you to a programming language, which was obviously Scala. So I called it Scala, your first programming language. And I hope that you were some of the people who watched it and this actually was your first programming language, because otherwise it was just way, way too slow. After over 20 videos of this initial Scala series, I realized that an ongoing project would be beneficial to progressively learn instead of having completely separated videos with dedicated topics. And so I designed the Homegrown collection series to introduce you also to some computer science terms like algorithmic complexity, and also to talk about fancy things like continuations or trampolines and even streams. By now, we have covered most of the things that the typical modern programming languages have to offer, except for concurrency, of course. And so the next thing that I wanted to do was to, well, obviously cover concurrency, but also to start going outside of the programming language and discover other things. I wanted to have videos about files and file systems and networking and the whole OSI model, the databases. I actually wanted to build my own, and then web services and so on. And I will create them one day, but not now. The thing is that these explanatory videos, they take forever to prepare, and also this whole sequential notion of them, I have to be able to look up like 10 videos ahead. At least until now, I always had a roadmap with the next 30 videos or so. And so it takes forever to prepare, and also they get so long that I guess everyone here, including this guy, would appreciate if they would be a little bit shorter. What I'm trying to say is that I need a break. And when I say I need a break, I don't mean that I will stop making videos. Hell no. All I'm saying is that the upcoming videos are going to become less sequential, less long, less introductory, and hopefully more fun. I don't have an exact roadmap yet. I just want to grab a few libraries and make a few cool videos about them. Also, I want to make a few videos dedicated to tooling and also maybe just create a few hands-on projects. Now, until now, anytime I built something for you guys, I made sure that there was a video before that explaining everything that you need to know. And this basically stops now. Not forever, but for quite a while. It's not going to be sequential anymore. So the next video might be about some super simple Git commands, and the video after that could be about some major big ass client server thing. It won't be, but you get the idea. Now, if you're someone who actually discovered my channel without prior programming knowledge, don't worry. One day we're going to go back to this path and you're going to catch up. Also, I know that a lot of you guys joined during the Monad series and you want more of these functional programming videos, and they're going to come as well. So don't worry. All right, enough talking. As always, it's been Vlad, devinside.com. Don't forget to like this video if you did, subscribe if you want to improve the developer inside you, and if you find my videos valuable, consider supporting me on Patreon, and then maybe one day I can actually start creating content full-time. And most importantly, take care.